So this video refers to Lecture 9, which is looking at centroids and centres of gravity, and it's the first video in this series for Lecture 9, and it's thinking about locating a centre of gravity. So a centre of gravity, if you imagine a shape that's not a simple shape, so an unusual shape, then your centre of gravity is often shown as a point labelled with a G. And if we were to want to use the resultant weight of that shape, then we would display it acting at our centre of gravity. So our weight, or our mass times gravity, would act at our centre of gravity. And it's very useful to be able to identify where that is, because if we're using a resultant force as part of a larger question, if we want to put the weight at the centre of gravity, then we need to know where the centre of gravity is. So in the lecture notes for Lecture 9, there's a series of equations. If you look on slide 7, you'll see there's an equation to find the x-coordinate. So for the centre of gravity, the x-coordinate would be shown like that, x bar. Similarly, the y-coordinate would be y bar and the z-coordinate z bar. And the centre of gravity, the x-coordinate would be the integral of x with a tilde on top, that wiggle is a tilde, dw over dw. So what we're saying there is we're saying the x-coordinate of our centre of gravity is going to be the central location of the piece of it that we're considering. So we're going to integrate, we're breaking down into very small pieces. X tilde is the centre of that piece, and I admit I've missed the centre of that piece there. dw is the weight, and obviously the integral of dw is the weight of the whole object. And for y, you'd use y bar and y tilde. For the z coordinate, if we're doing 3D, you'd use z bar and z tilde. And if we replace our w's with m's, so for instance finding the x-coordinate centre of mass, which will be the centre of the shape's weight as well. So to find the centre of mass, we do exactly the same thing, apart from we're using dm instead of dw. And we can do the same thing looking at replacing with dv and find a geometric centre. So to find a centre of gravity, we use our top equation. To find a centre of mass, we use our bottom equation. For this just being the x-coordinate example I'm showing you. And for a centroid position, a geometric centre of a shape, we would replace that with a dv of volume or dA in area, depending on if it's 2D or 3D. If you look at slide 9 of the lecture notes, there are some common centroid positions for some common shapes. So, for instance, a rectangle. The centroid is halfway in the height and halfway in the width and halfway in the height. So, x bar is going to equal width over 2. That's a fairly easy one. On the website and through Blackboard, you can access a lot more common shapes, and they'll also be in the exam paper if you acquire them. Quarter circles, semicircles, circles, and it tells you where the x bar, the y bar position are, and it also tells you how to calculate the area. But if we go on to look at the example that begins on slide 11, I'll just briefly sketch it and then I'll talk you through it. So we're asked to find the area of the bit that I'm just shading in now. Okay, so we're asked to find the area of that shape. What we're going to need to do, if I just remove some of those lines, this bit I've just shaded in, is still the bit we're interested in, I just need to sketch onto it. We're going to find a series of different pieces of information. So we know that, for instance, the x bar coordinate is the integral of x tilde dA over the integral dA. So we're going to consider, if we're integrating across this length, we're breaking it down into very, very small strips. Each of those strips is a width, dx, and is a height, y. And the centre of that strip will have an x coordinate and a y coordinate. So the centre of that strip will have x and y coordinates, x tilde and y tilde. And we know that the y coordinate, y tilde, is going to be y over 2, because it's halfway up that strip. So if that's y, the centroid position of just that strip that we're breaking our shape into when we integrate will be y over 2, will be just there. So what we now need to do is we now need to take the three terms from our equation and start putting them together. That should be a tilde, sorry. Well, if we're considering integrating this whole shape, we're going to take this strip, which is of width dx, and we're going to move it all the way along. So wherever our x position is, our x tilde will just be a position x along the shape, and we're going to move that along the shape, obviously, as we integrate. So our area is going to equal, for that rectangle, y, the height, times the width, dx. Well, y, we're told for this line, is x cubed. So that's the same as x cubed dx. Our x tilde position, we've already said, is x. Our y tilde position, we've said, is y over 2. And y is x cubed, so it's x cubed over 2. We can now start substituting things into our equation. First of all, for the x bar position, so we've said x bar is the integral of x tilde dA over the integral of dA. So the integral between 1 and 0, because this is 1 metre, we're moving our strip 1 metre in distance, and we're going to do the integral of x tilde, which is x, dA, which is x cubed dx, over the integral between 1 and 0 of dA, which is x cubed dx. It's the integral between 1 and 0 of x to the 4 dx over the integral between 1 and 0 of x cubed dx. Jump to the next page. That's going to be x to the 4 becomes 1/5 x to the 5 between 1 and 0 over 1/4 x to the 4 between 1 and 0. Substitute 1 into there, and I'm going to get 1/5 minus 0 over 1/4 minus 0. That equals 0.8. So our x coordinate of our centre of that position, our centroid location, our geometric centre, is going to be 0.8 metres in the x direction. So somewhere about there.